Okay. Good afternoon, everyone. Thank you for coming today. And my name is Fang-Yu Rao. Currently a PhD student working with Professor Bertino in Computer Science Department. And today I'm going to present our work regarding private record linkage. And this is a work, a joint work with other researchers from A-Star Singapore and UT Dallas. Yeah. So here today, the outline of my talk today will be like the following. Like at the very beginning, like I will give the definition of the problem we are going to solve, which is private record linkage. And I will also introduce to you some of the background techniques we are using to construct our solution. Then I will briefly introduce a very closely related work which does not satisfy all the privacy requirement. Finally, I will provide you with a novel framework for a private record linkage. Also give the corresponding experimental results to demonstrate the efficiency and effectiveness of this framework. And so here. So at the very beginning, I would like to say what is like private record linkage. Actually, private record linkage is a technique allowing multiple parties to identify individuals corresponding to the same entity in the real world, or individuals with very similar attribute values. So here we assume that like each party has its own schema, and in our problem setting, we assume that there are only two parties involved, and we will use Alice and Bob to denote these two parties participating in the process. So these two parties will use, each having its own schema, will use their predefined linking attributes to find out those records they have very similar attribute values. For example, here these two parties would like to use age, weight relationship, and occupation to find out the individual with very similar attribute values. And here we also consider each record in the database as a d-dimensional point. So how do we consider two records match each other? One of possible rules we can come up with is the following. We can actually use the weighted squared Euclidean distance to measure the similarity or dissimilarity between any two records. And we say these two records match each other if their weighted square Euclidean distance is upper bounded by a predefined threshold theta. And here, say Wi would be like the weight for the ith attribute. Theta would be the threshold predefined by both parties. And U and L denote the lower and upper bounds on each dimension. So a naive solution to solve this problem would be like for each party to revealing its private input or its database to the other party. However, we know this will raise privacy concern because the privacy of those non-matching records will also be revealed to the other party simultaneously, and this is not what we like to have. So one approach to solving this problem is to borrow some techniques from the crypto community. And this technique is called secure multi-party computation. Here, since we are dealing with the two-party case, then we will mainly focus on the two-party case, in which Alice and Bob, each having its private input, will be able, through the invocation of secure multi-party computation, will be able to compute the function output of their joint private inputs, such that in the end of the protocol, only the designated output is revealed to each party, namely Alice and Bob. A very famous approach to implement secure two-party computation is through the use of Yau-Scarborough circuits. In this protocol, actually, Alice will act as a circuit generator, and Bob will act as the circuit evaluator. They will together perform computation on their respective private input and get the final output. This approach can be proved to be secure, but unfortunately, the cost of this kind of approach is prohibitively high. To make this clear, we give some concrete numbers. Here, actually, according to our experiment, the matching of two data sets, each having only 6,000 records with 5 attributes, it would take 40 days to finish the comparison on a pair of i7 CPU. So we really need to, some approach to eliminate or obviate some unnecessary secure comparison between records. So before explaining how to do this, let's review a privacy concept called differential privacy. Okay, differential privacy, intuitively requires that, given a database as the input, the output of any function computed on this input database should not change significantly whether or not any individual joins or leaves the database. So to be precise, if we are saying that a mechanism or algorithm M satisfies epsilon differential privacy, what we really mean is that the ratio of the probability of any outputs before and after any individual joins or leaves the database is upper bounded by e to the power of epsilon. Like e is the natural number, like 2.71, something like that. And here we have a concept of neighboring database. If we are saying that two databases are neighbors, then we are saying that they only differ at one tuple. And we also know, it is also well known that epsilon, differential privacy could be achieved. When we are going to release or publish the number of tuples in a database, it will be enough to add a Laplace noise of scale equal to 1 over epsilon, as we can see here. And that one in the numerator is called sensitivity, which in the case of counting the number of tuples in the set is the max change to the counting function after any individual joins or leaves the data set. As we know, when we are counting a set, the maximum change to that counting function could be only 1. after any individual joins or leaves the dataset. And differential privacy also has the nice property of composability, which means the output of a mechanism satisfying epsilon 1 differential privacy, if we use this output and feed this output into another mechanism which alone satisfies epsilon 2 differential privacy, if we are doing things like this, then at the end, the output O will satisfy epsilon differential privacy as a whole, where that epsilon would be the sum of those epsilon I, for I from 1 to 3. I mean, this is just a nice property of differential privacy. So next, let's take a look at a very closely related work which tries to address the efficiency issue I mentioned earlier. This is a work published in 2010 in a very famous database conference. So in their work, what they propose is for both parties to first partition their data space into disjoint subsets. And they will also publish the information of those bounding boxes as well as the noisy number of tuples for each subset, disjoint subset. So how to produce the noisy number of subsets for each subset? Like, to do this, actually, each party has to draw a random number from that specified Laplace distribution to and then add that noise to the true count for each subset. For example, Alice here she draws a random number from that distribution, and that random number happens to be -1. If that is the case, then Alice will have to randomly suppress one record from her data set. Say we take a look at the leftmost subset, C11. Alice, in this case, will randomly suppress X3, which is one of her records in that subset. We note that this record will not participate in the secure comparison later on. And if that noise used to perturb the size of a subset is positive, then Alice will have to generate one fake record to participate in the secure comparison later on. It can be seen that with the information of those bounding boxes, because the information of those bounding boxes are actually revealed to the other party in the clear. That is to say, unnecessary secure comparison could be avoided. For example, Alice here would know that her record X1 does not have to be compared with any record residing in Bob's subset C22 because they are actually far away. And that's also the reason why the efficiency could be improved somehow, because we actually could avoid some expensive secure comparison by revealing the bounding box information. So in the second step, they will just carry out the secure matching and find out what is their records in common. So, but actually there is a very subtle problem within this approach, which I might not have time to explain today, but in summary, actually we have proved that if, both pieces of information are revealed, then differential privacy cannot hold in the end. That is to say, if both parties reveal the bounding boxes information as well as the the noisy counts for each subset, then together with the information of matching results after the secure matching, more information could be inferred, and that makes differential privacy not hold anymore. So to address this issue, what we are going to do is to introduce a third-party Charlie. This Charlie will have to coordinate the matching process without knowing the matching results. So how do we do that? So our protocol actually consists of 3 steps. In the first step, it's like the previous related work. Alice and Bob will have to partition their respective datasets into disjoint subsets, and each of them has to publish the bounding boxes as well as the noisy counts for each subset and the encrypted records within each subset. Those pieces of information have to be sent to Charlie. But here we notice that Bob here will not see Alice's bounding box information, nor does Bob, meaning that Bob does not know Alice's bounding box information either. And in the second step, Charlie will have to coordinate the matching process because Charlie is able to see those bounding boxes in the clear, and Charlie will know that records from C1 might have potentially matching records in C2. So after performing distance preserving randomization on the encrypted records in these 2 subsets, Charlie will have to return those randomized encrypted records back to Alice and Bob. In the third step, Alice and Bob will jointly perform secure matching protocol without the matching result being known to Charlie. So what we have achieved is that in the end of protocol, the matching results are not known to Charlie, while in the first step, like the bounding boxes information, Alice's bounding box are not known to Bob, and Bob's bounding boxes are not known to Alice either. So in this setting, we actually avoid the inference attack, which happened in the previous related work. So here we emphasize that Charlie has to randomize the encryption of records X and Y. Suppose that according to the bounding box information, Charlie knows that an encrypted record encrypted under Alice's public key, and the encrypted record Y encrypted under Bob's public key might match. Charlie has to randomize this potentially matching ciphertexts. That is because we want to prevent the inference attack in the case where X does not match Y in the end, because Alice might know how many times one of her records X has been securely compared with Bob's records. We actually want to hide this piece of information in the case when a record X does not match record Y. So how can we do that? Actually, we will use a famous homomorphic encryption scheme called pair encryption, having the following nice property, meaning that if we multiply the ciphertext of M1 and M2, two messages, we are able to create a ciphertext corresponding to M1 plus M2. Using this property, Charlie is able to perform that distance preserving randomization. So recall that, suppose that record X is encrypted under Alice's public key, and record Y is encrypted under Bob's public key. Using the homomorphic property I have just described, Charlie can randomly select a random number for each dimension and create a pair of randomized records, X prime and Y prime, while preserving their relative distance. Here we can see X is a two-dimensional point and Y is a two-dimensional point. Charlie randomly select gamma 1 and gamma 2 and add these two numbers to the corresponding dimensions. And in the end, Charlie is able to create an encryption of X prime and an encryption of Y prime, encrypted under Alice and Bob's public key respectively. And here we can see that the distance between X and Y is actually preserved. And even Alice is able to decrypt that ciphertext corresponding to her record X. What she can see is only the random number, and so does Bob. So what we have seen is that Charlie is able to create an encrypted version of X prime and Y prime such that the distance between X and Y is equal to the distance between X prime and Y prime, the randomized records. So what we are going to see next is that I would like to establish the fact that actually X prime matches Y prime will be true if and only if big delta is upper bounded by big theta. So recall that what is our definition of two records matching each other? Actually, it's the first inequality we can see in the first formula here. It can be easily seen that the first inequality is true if and only if big delta is upper bounded by big theta, where big delta is the squared weighted Euclidean sum of these two randomized records, and big theta is the square difference between upper and lower bounds multiplied by theta. So one solution for these two parties, Alice and Bob, to match the records is that Bob can jointly compute with Alice the encrypted big delta under Alice's public key and send this ciphertext back to Alice. since Alice has her own private key, so she can use her private key to decrypt this ciphertext and get delta. And Alice will know that whether or not this inequality holds. If this inequality holds, then she knows that, well, X and Y match each other. However, in the case of non-matching, this delta actually reveals sensitive information. At least it reveals Alice's record, the distance between these two randomized records. If we even want to hide this piece of information, what we have to do is for Bob to jointly compute an encryption of delta plus rho, encrypted under Alice's public key. Here we notice that rho is a much larger random number compared to delta, so that it can safely mask the true value of delta, the left-hand side of that inequality. So actually Alice here, he can get big delta plus rho, and Bob has big theta plus rho, where rho is only known to Bob. Now they are able to perform secure comparison without Alice knowing the distance between these two randomized records. That's how the secure matching is done. So below are the properties of our protocol. First, what we can guarantee is that for each pair of records being securely compared by these two parties, the decision rule we just mentioned at the very beginning is correctly computed. And the second guarantee we can provide is that at the end of the protocol, what Charlie sees remains limited to those bounding box information and the noisy count of subsets, nothing else, because the matching results are hidden from Charlie, only known to Alice and Bob. And the third guarantee we can provide is that at the end of the protocol, Alice and Bob only know the matching records plus the total number of secure comparison performed. That's the three properties we can guarantee. So we will also discuss how our protocol enables Alice and Bob to partition their data space. But first, let us take a look at this non-dominating rule which we are using to build that space partitioning algorithm. So recall that to satisfy epsilon x differential privacy, when we are going to publish the number of tuples in a set satisfying differential privacy, we can use Laplace noise, or we can draw a random number from a Laplace distribution with scale equal to 1 over epsilon x. And we also know that the expected absolute value of the noise is exactly equal to 1 over epsilon x. Here, what we can see is that if we have a higher epsilon x, actually the noise generated, the expected noise magnitude of noise generated would be lower, which in some sense maintain the data quality. Like if we have less noise, then we will have better estimate of how large this subset could be, or how many tuples are actually inside that subset. Sometimes we also call this epsilon x the privacy budget. And actually we can see that there is a trade-off between privacy and data utility here. And non-dominating rule actually further requires that the following inequality is true. When counting a set C with estimated count S tilde, actually we would like to make sure that the ratio of the expected Laplace noise, expected absolute value of Laplace noise to that noisy, to that estimated count S tilde is upper bounded by eta. In English, actually, we would like to say is like we do not want, in order to maintain data utility, we do not want the magnitude of the noise being too large. So here, after seeing the non-dominating rule, we are ready to present our algorithm to partition the data space. So our algorithm will start from the root and partition the data space recursively. Basically, we are going to build a search tree over the database. And our space partitioning algorithm consists of two stages, probing and populating. And given the total privacy budget eta, we will divide it into two parts. One half of that budget will be assigned in the first stage, and the other half will be assigned to the second stage. And we also assume that given a tree node being processed, we have already had the following three pieces of information regarding this tree node. First, the bounding box records, and the records inside that bounding box, and also the currently available probing budget, together with the noisy count S tilde. Our goal is to count the size of the two child nodes of that tree node C. So how to count this? How to count the two children of this tree node C? Actually, we have to make another assumption. We have in this paper, it's just a heuristic. We actually assume that two children of this tree node C contain approximately the same number of records, which is S tilde divided by 2. And now we will apply the non-dominating rule to compute how much privacy budget I should spend to count the number of records for each child of this tree node C, because we do not actually want to spend too much budget, in some sense. So let's take a look at how things works, how our algorithm works in the first stage, the probing stage. So suppose that we are processing a tree node with the estimated size equal to 29,000, and the current privacy budget is equal to 0.5. What we are going to do is to apply the non-dominating rule to see how much budget I should spend to count each of the child nodes for this currently tree node being processed. So according to the formula of non-dominating rule, it says to accurately count the number of records inside each of its child nodes, we should at least spend 0.07 of privacy budget to count each child node. And since right now we have the currently available budget is equal to 0.5, we are able, we have enough budget to do this. So we will split this tree node into 2 child nodes along the dimension of gender, say male or female. And we will use 0.07 to count each of the child node. What I meant is we will use 0.07 as the parameter to that Laplace noise Laplace distribution, and we will sample a noise from that distribution. And in this case, let's take a look at the left child node. Here we can see that in this case, for the left child node, the noise I have drawn is actually positive. And that's why the true count S, although it's equal to 9,164, the estimated or the noisy count for this child node is actually equal to 9,669.5. Of course, we will do the rounding actually. And for the right child node here, actually the noise we have sampled is negative. So in this case, the published noisy count for this child node would be like 19,934, which is less than its true count. And also we have to subtract that 0.7 from the available privacy budget. So the available privacy budget for both the left and right child nodes would be 0.43 instead of 0.5 previously. So let's consider a case when we do not have enough privacy budget. So like here, the current node we are processing only has like available budget of 0.018. And when we apply that non-dominating rule, we'll find out that, well, we do not have enough budget, because according to that rule, we have to have 0.211, which is larger than the currently available privacy budget. So how do we do right now? Actually, we just split this tree node into leaf directly. But another question raises, how many leaves should we grow? Actually, we need to make sure that we do not grow too many leaf nodes. Again, how many leaf nodes should we grow from this tree node currently being processed? We will again apply that non-dominating rule. And according to our calculation, we should not produce more than 4 leaf nodes in this case. So we know that we will be going to split this current tree node into no more than 4 leaf nodes. What we will be doing would be use a uniform grid to partition the data space along each of the 2 chosen dimensions. And we will produce the following 4 subsets. And here, like S denotes the true number of records within that subset, and S tilde denotes the noisy number. Noisy number of records within that subset. Here is how we are going to how our algorithm works. So we also have some like experimental results, and according to that results, actually we found that actually our protocols are much better in terms of efficiency and effectiveness. So here is some results. First, the cost of that space partitioning algorithm is pretty low. Like if there are 6,000 records within each database, then the cost of partitioning is only 35 milliseconds. However, the cost of distance preserving randomization is pretty high. According to our results, like it will take Charlie at least 33 milliseconds to randomize one record pair. And the cost of secure comparison per record pair is even higher. Like it will take almost 0.1 second for Alice and Bob to securely compare their randomized records. However, we noticed that this kind of process could be highly parallelizable. For example, on the left-hand side, we can see that it will take around like 45 hours if we only have one pair of i7 CPUs. However, if we have like 100 pairs of Intel Xeon CPUs, then the time could be reduced to within 2 hours. So we also have some experimental results regarding the time we could save by using our algorithm. We also compare our algorithm with other state-of-the-art schemes, which also, which is claimed to be satisfying differential privacy. So here, I would like to emphasize that here actually by using our algorithm, the time both parties will spend on the matching process will be around like 20 hours. However, when using the schemes provides, the space partitioning schemes provided by other two papers, it would take at least 70 hours for them to finish the linking process, which actually demonstrate the efficiency of the space partitioning algorithm I have just described. And also, our scheme also achieves high recall rate. It can be seen that given all possible dataset sizes and all possible privacy budgets ranging from 0.1 to 1.0, actually we could achieve the recall rate around 95%, which meaning that 95% of the matching record pairs could be retrieved after executing our proposed framework or protocol. Notice that why we will have missing tuples here, meaning that the recall is not 100%. That is because in order to satisfy differential privacy, the number of records will not, is not accurate. Recall that we actually have to sample a random number from the Laplace distribution, and if that random number sampled happens to be negative, we have to actually randomly suppress some records and prevent these records from participating in secure comparison later on. That actually results in a recall less than 100%. But anyway, according to our experiment, it can be seen that our algorithm, our space partitioning scheme is very effective. So here in this work, we actually provide a framework, a novel framework for private record matching, which is actually provably secure, and it's also efficient and effective. So for the future work, we plan to work on the matching of structured data like trees or graphs. Yeah, so here, this is my presentation today. Thank you for coming. And if you have any question, you can ask me right now. I know, the talk is a bit technical and might be also boring, but yeah, thank you for coming today. Anyway, thank you very much. So any question, or we can just call it a day, or okay. So yeah, thank you for coming today.